this section, we're going to talk about one of my favorite examples from the whole course, which is seriation in archaeology. This is just doing sequence dating of archaeological remains. And so here we are in section 2.3, and symmetric matrices are going to play a big part in this. We haven't even talked about what they are yet, but we will. Let's just remember for a minute where we've been in the last couple of sections. We've really talked a lot about the algebraic theory of matrices. We've talked about adding two matrices together. We've talked about taking a scalar and multiplying it by a matrix. And we've talked quite a bit about when and how we can multiply two matrices together. This was sort of a big deal. It's not always possible to do, but when it is, what kind of things follow. And you'll remember that importantly, we learned that AB does not necessarily, we'll say, equal BA. Sometimes it does, but a lot of times it doesn't. And so this was a big difference between real numbers and matrices, that the commutativity of multiplication doesn't hold with a matrix algebra. Now we're going to take some of these tools that we have, and we're going to introduce some new ones also, and we're going to solve a big problem of ordering graves at a grave site. And we're going to use the pottery that's in each grave to help us figure this mystery out. And this application comes out of our textbook, Linear Algebra with Applications by Gareth Williams. So our story starts with an archaeologist named Sir Flinders Petrie. He's living in the late 1800s, and he's doing archaeological work in what was prehistoric Egypt. He comes across a site, and it's a grave site. And in this grave site, there are over 900 graves. And like any good archaeologist, he wants to be able to find the dates for things and to be able to do some sort of ordering of these graves. You know, he knows that not all 900 came from the same time period, but how could we figure out when, different graves when they came from? One thing Petrie does know is that the graves range from between 6000 BC to 2500 BC. But that's kind of a big span of time. I mean, if you think of that 3,500 years, think about from our time period, what was going on 3,500 years ago. That's 1500 BC. And so there's a big span of what could have been happening. And so it's natural that he wants to be able to order these graves chronologically and learn things about different time periods. So we're going to think of this problem in a general way. What if we were that archaeologist that came across this field, and actually having the tools that we have, this new really powerful tool of a matrix, how could we use that to help us to order these graves? So that's our goal, is we want to order these graves chronologically. So we're going to work on this goal to order these graves chronologically, and the tools that we're going to use are both matrices, and the other important hint or tool that we're going to use is the pottery that is buried with each of these graves, these individual graves. And so here are our tools, matrices and the pottery. And I just love this application because it just highlights that you have this massive amount of data, and there's just no way that your brain can, start ordering these 900 graves. Even if you're making lists on paper, the data just becomes overwhelming. And the magical thing is that matrices will take this data, and a few extra tools we're going to use, something called the transpose of a matrix, which we'll see in a minute. The information and the results just almost fall out of the matrices and give us so much ordered data that we can get a good guess as to the order of these 900 graves. As we work on this goal to order the graves chronologically, we're going to make one assumption. And this is the assumption we're going to make. Two graves with similar contents are more likely to lie close together in time than two graves with little in common. So thinking of a timeline, if you're at 6000 BC, 6000 and maybe 5500 BC compared to say 2500 BC. Graves from these time periods will have more similar pottery than two graves from each of these time periods. And so as we look at these graves and we examine the pottery, when we find pottery that's similar, we're going to assume that those graves are closer together on the timeline. And that sounds like a pretty reasonable assumption. We're going to baby step our way into all this grave ordering. We're going to look at an example with just 4 graves and 3 pottery types. We're not quite ready to tackle 900 graves yet, but we'll look at 4 graves and 3 pottery types. And in the matrix I'm going to use, I'm going to let each row represent a different grave. So grave 1, 2, 3, and 4. So here are the 4 graves that I have. And within just these 4 graves, there are 3 different pottery types. So these are 3 different pottery types that are distinct enough that they're probably coming from different time periods. And the way I'm going to use this matrix is it's going to help me count, which type of pottery I find in which grave. So in grave 1, for example, I find one of the pottery type 1. So I'm going to put a 1 here. I don't find any of this second type of pottery, so I'm going to put 0 here. And I do find some examples of the third type of pottery. I might find multiple types of that third type, but I'm just going to put 1 to indicate it's present, it's there. I'm going to do the same thing for all of the different graves. I'm essentially going to count which type of pottery shows up in which grave. So from this second row, I see that in my second grave, I only had pottery that was of the first type. I didn't have any of these guys. And in the third grave, I didn't have any pottery type 1, but I did have some pottery that were similar to type 2 and 3. And so actually already I can see something about graves 2 and 3. They don't have any pottery in common. And so these 2 graves are further apart chronologically. And then grave 4, it doesn't have any pottery type 1, but it does have pottery type 2 and nothing from pottery type 3. Okay, now we're going to do some matrix algebra that isn't totally obvious why we want to do it at first, but as we go through this example, you'll see how valuable it is. We're going to swap the rows for columns and the columns for rows, and then we're going to multiply those 2 matrices. So every row in our original matrix is now going to become a column. So we're swapping the rows and columns, creating a new matrix, and we're going to take this original matrix and the new matrix that we create, and we're going to multiply them together. So here's our original matrix. And I said I wanted to create a new matrix where the old rows are the new columns. So this first row will become the first column of the new matrix. And then I'm going to take this second row and make it the second column of this matrix. And I'm going to take the third row and make it the second column of this third column of this matrix. So 0, 1, 1. And last row right here, I'm going to make it the last column here. Okay, so we've done this first step. We are going to multiply these 2 matrices together now. Before we do, let's talk about what things in this new matrix are representing. Now this column is representing grave 1. This will be grave 2, grave 3, and grave 4. And then the rows are just representing what the old columns were representing: pottery type 1, pottery type 2, pottery type 3. Okay, everything's good. And remember that we want to multiply these 2 matrices together. Can we even do their sizes match up? It looks like it's fine. We've got these rows matching up with these columns, so they're the same size, and that's all we need to multiply, so we can do it. Before we do the multiplication, I am going to tell you there's a name for when we swap rows and columns of a matrix. This is the transpose of our matrix A. Wait, did we ever call it A? Okay, let's go back and call it A. So we'll call this matrix matrix A, and this is now the transpose of A when you swap rows and columns. And the notation when you're talking about the transpose of A is A with a little t up here. That's a little too close there. Let's do A with a little t right there. That tells us we're talking about the transpose of A. Okay, so we're now going to multiply these two matrices together. And we'll take this row and operate it with this column with matrix multiplication. So 1 times 1 is 1, 0 times 0 is 0, add to that 1 times 1. So we should get 2 in this first entry. And then we're going to take this first row and multiply it by this second column. So here we get 1 times 1 is 1, 0, and this will be a 0 also. So we only get 1 here. But this is where we want to pause, and we want to think about what does this represent. This is grave 1, and the pottery types that were in grave 1. This is grave 2, and the pottery types that are in grave 2. Grave 1 and grave 2 had this pottery type in common. They had no other pottery types in common. Whoa. And so there was a 0 here, there was a 0 here. Neither of them had pottery 2. But even though grave 1 had pottery 3, it didn't matter. Grave 2 didn't have pottery 3. So what this number here is doing is counting how many types of pottery graves 1 and 2 have in common. Whoa, that's a big deal. This number will count for us how many types of pottery grave 1 and grave 2 have in common. Okay, so we've made note of that here. This counts the number of pottery types that grave 1 and grave 2 have in common. Let's keep going with our multiplication. We still need to do this row by the third column. And so we have 1 times 0 is 0, 0 times 1 is 0, and 1 times 1 is 1. So this number is 1. Well, it's no surprise. This number is actually counting the number of pottery types that grave 1 and grave 3 have in common. If you think about where the row is coming from and where the column is coming from, anytime graves 1 and grave 3 have something in common or have the same type of pottery, they'll both have a 1 there, and that 1 times 1 will get picked up. If one of them doesn't have it, then there's a 0 somewhere in that product, which will knock it out. So this number is going to count how many pottery types grave 1 and grave 3 have in common. And we knew that from the very beginning, that grave 1 here and grave 3 here had pottery type 3 in common. There was only one pottery type in common, so they had 1 in common. What should we expect this number to be right here? Well, it's going to represent the number of pottery types that grave 1 and grave 4 have in common. How many do grave 1 and grave 4 have in common? Let's see. Looking at these two, they have 0 in common, so we should expect a 0 right here. But let's do the multiplication. Okay, so we'll do this multiplication, and we're going to take this row times this column here. 1 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and it's what we thought it was going to be, that it is 0. And that 0 is counting the number of pottery types that grave 1 and grave 4 have in common. We can see how this is going to play out for the rest of this matrix. In this row, we're going to see what grave 2 and other graves have in common. And in this row, we're going to see the common graves, or the common pottery types in grave 3 and other graves, and so on. And this is really what I was interested in counting, because the way that we tell if two things are closer together on the timeline is if they have similar contents. And the higher this number is, the more similar their contents. And you can imagine in like a 900 by 900 matrix that maybe you'll get two graves that have 37 pottery types in common, and that might indicate that they're very close on the timeline. But let's keep going with our multiplication. We'll take the second row times the first column, and we'll get 1 times 1 is 1, 0, 0. So we get a 1 right here. And then we take this second row, second column, and we get, looks like a 1. And the second row, third column, we have 0, 0, 0. So that guy is 0, and we'll take the second row, last column, and we get a 0 times 1 is 0, 1 times 0 is 0, 0 times 0 is 0. And we can go through with this row, all the columns, and this row, and then all the columns, and we'll end up with this matrix. This is the product of A and A transpose. This is a very special matrix. It's counting the number of pottery types that different graves have in common with a different grave. So this element here, this is the A34 element. Actually, that's kind of confusing because we have a matrix called A. Let's just call it the 3-4 element. And where did it come from? It came from, that element came from taking the third row, grave 3, and multiplying it with the fourth column. So this was telling us how many pottery types grave 3 and grave 4 have in common. And we can kind of see that. We can see that they only have pottery type 2 in common. We knew that from the original matrix. And so they only had one type in common. You know, you can think of look at this matrix and think, well, what's the big deal? I can just kind of look at here and see how much they have in common. But when you have not 4 graves, but 900 graves, and just keeping everything, keeping track of everything, this matrix becomes really powerful in telling us exactly which graves are really close to each other. So here we see the 3-4 element counts the number of pottery types grave 3 and grave 4 have in common. From that, you can probably generalize, you know, the IJ element of this matrix will tell us how many pottery types grave I and grave J have in common. Okay. Now, how do we take a matrix like this and actually order the graves? I mean, we have these numbers sitting here, but how is that going to help us decide, you know, which graves are closer chronologically? So I'm going to move these guys over a little bit because I want to give us a little space here to interpret all of these entries in this matrix. We already decided that this number right here told us that grave 1 and 2 had one pottery type in common. This element here told us that graves 1 and graves 3 had one pottery type in common. This right here told us that 1 and 4 had 0 pottery types in common. Then I'm going to move to this element here. This is the 2-3 element. So this is going to tell us how many graves 2 and 3 have in common, and they have 0. And graves 2 and 4 also have 0 pottery types in common. So why did I skip around? Why did I skip these guys? Well, this is the 2-1 element. This would tell us how many pottery types grave 2 and grave 1 have in common. Essentially, we already have that because the same number of pottery types that are common to 1 and 2 are common to 2 and 1. It's a symmetric relationship. If the pottery is common to graves 1 and 2, it is also common to graves 2 and 1. That order doesn't matter. So this number will always, in fact, be exactly equal to this number. And you're seeing it already. This number is the same as this. This number is the same as this. This number, same. This number, same. This number, same. So we're getting a symmetry. And we'll talk in a minute about what the diagonal numbers represent. But for now, let's see what I'm missing here. I've got 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. I think I need 3 and 4, how many they have in common. So I'll go to the third row, fourth element. This will tell me how many graves 3 and grave 4 have in common. So now I'm going to look at this information and try to come up with some sort of chronological order. And I'll start with 1 and 2. They at least have one piece of pottery type in common, so they're probably not totally far apart on the timeline. So 1 and 2. 1 and 3 also have something in common, so they're probably pretty close. But I want to see, you know, are 2 and 3 close together? Well, 2 and 3 have no pottery types in common, so they're less likely to be close on the timeline. So 1 is close to 2, and 1 is also close to 3. So one possibility is a relationship like this, that, you know, maybe 3 came before, and then we had grave 1 was a certain time period, and then 2. All we know is that 1 has things in common with both of these. Okay, what about 4? What is 4's relationship? It really doesn't have nothing in common with 1, nothing in common with 2. It does have something in common with 3. So it's probably linked to 3 somehow. And this is a type of ordering of the graves. Now, do we know which direction it goes? Do we know that it, you know, follows this direction? Not necessarily. It could be that, or it could be the reverse. 2, 1, 3, 4. We just know in relation to each other the probable ordering of these graves. So this is it. This is the answer to the whole problem. This is our best guess at the ordering of these 4 graves chronologically. This right here is our likely chronological ordering of the graves, all based on this assumption that if 2 graves with similar contents, they're more likely to lie close together in time than 2 graves with little in common. Before we leave this example, I want to talk about these diagonal elements. What do they represent? Well, it's what grave 1 has in common with grave 1. And it has 2 pottery types in grave 1, so it has 2 pottery types in common with itself. This represents grave 2, how many pottery types are in there. This will represent grave 3, how many pottery types are in there. There are 2, we saw that from this matrix. And grave 4, there was only 1 pottery type in there. So these diagonal elements are counting the number of pottery types in each grave. The reason that we didn't need these elements so much down here is because they were already represented up in this upper right triangular section. If you had a very large number of graves and a very large number of pottery types, the work is similar. You take this grave, multiply it by its transpose, and you'll get entries that tell you how 2 graves compare, how many pottery elements they have in common. And that leads you to being able to order things in this way and order them chronologically. Let's pause here now that we've finished this example and articulate some of the theory that we've come across along the way, like transpose, symmetry, some other ideas. So we'll say let A be any matrix. When you swap rows for columns and columns for rows in that matrix, you get A with a little t. This is not a power. This t is representing the word transpose. So when you swap rows and columns, you get A transpose. And you can take the transpose of any matrix. It could be any size. It could be a column. It could be a column vector. It could be a matrix size 1 by 17, or it could be 32 by 3. It doesn't matter. There's no prerequisite. You can take the transpose of any matrix. So if our matrix A is this one here, and let's see, this is a 2 by 3 matrix, then A transpose we know will be a 3 by 2 matrix. And A transpose will be 1, 2, -5, 4, 7, 0. It is worth talking about the properties of transpose. This is an algebraic operation with matrices, so we want to talk about what properties follow from this operation. If you take 2 matrices and add them together and then take the transpose, that's the same as taking the transpose of each of them and then adding them together. If you take a scalar and multiply it by a matrix and then take the transpose, that's the same as taking the transpose of a matrix and then multiplying it by a scalar. If you take a matrix and take the transpose of it and then take the transpose again, what do you think you would get? This one I'm going to leave in the quiz for you to answer. What would the answer to this be? You take the transpose of a matrix and then take the transpose again. And one important one is if you take two matrices, multiply them together, and then take the transpose, this is equal to not A transpose B transpose, but B transpose A transpose. And there's a good proof of this on page 95 in the textbook. And there will be a question on the quiz about that proof, so be sure and look at page 95 for the proof of this. This is the one that's, of all of these properties, this is probably the most interesting as to why this has to happen. Another thing that we saw in the grave example was the idea of symmetry. So we want to come up with a definition of when a matrix is symmetric. So we'll say by definition that a matrix A is symmetric if, well, how would we describe this? We know we saw a symmetric matrix back here, this guy, where, the 2, 1 element was the same as the 1, 2 element. the 3, 1 element was the same as the 1, 3 element. So how could we write that down formally? We could say that Aij equals Aji for each element that's not on the diagonal, but there's actually an easier way to define this. If you took this matrix and took its transpose, think about what you would get. So go ahead and mentally transpose this matrix. You would get the exact same matrix back, right? Because the rows and the columns, row 1 is the same as column 1, and row 2 is the same as column 2. So in this matrix, this symmetric matrix, the transpose is the same as the original matrix. So maybe a good way to define symmetry in matrices is to say that A has to equal its own transpose. There are mathematicians who think these are the single most important class of matrices because of the range of applications for symmetric matrices, and we'll see more of them as we look at more examples. But this is a really important class of matrices, matrices which are symmetric. By the way, these matrices all have to be square matrices. So that's just from the get-go that you can't talk about a symmetric matrix without it being square. Okay, the last thing I want to define before we move back to more examples is something that we haven't talked about yet. It's something called the trace of a matrix. Sorry, before we move on, I do want to do one example with a symmetric matrix where we're given this matrix and we want to complete this so that it stays symmetric. And so we need to figure out what number goes right here. This is the 2, 3 element. So it's symmetric, so it has to be the same thing as the 3, 2 element. So that would be -2. This right here is the 2, 4 element. So I would look for the 4, 2 element. So that has to be 6 to stay symmetric. This is the 4, 1 element. So I just need to look at the 1, 4 element. It's got to be the same thing. And lastly, this is the 4, 3 element, so I would go to 3, 4 to find out what the number should be. Okay, and so now I have a symmetric matrix. Okay, now we're ready to talk about the trace of a matrix. So the trace of a matrix A, which is written like this, is the sum of the diagonal elements of A. And this too only works for square matrices. So here I have a matrix A, and it's a 4 by 4 matrix, so that's a square matrix. Awesome. And I can find the trace. I just need to add up all these guys here. So the trace of matrix A will be 5 plus 3 plus 0 plus 1/2. So the trace of this matrix will be 17 halves, or 8.5. Before we leave, I want to go through one last example of grave sites and pottery types. So the following matrix describes the pottery contents of various graves. Determine a possible chronological orderings of the graves and then the pottery types. Okay, so the second part is something new. The first part is what we've done before, a chronological ordering of the graves, but now they're also asking us to give a chronological order of the pottery types. All right, well, let's try the first one first because we sort of know how to do that one. So we'll do like we did before. We know each of these rows represent a different grave, so it looks like we have at least one more grave here. We have 5 graves and 4 pottery types. We're going to multiply this by its transpose, and that way it'll pick up which, between 2 graves, how many pottery types they have in common. Okay, here's the transpose, and now each of these columns is really representing different graves. We're going to go ahead and do the multiplication, and then we'll read off the information from that product. Okay, I've done the multiplication, or I did the multiplication on my calculator. This was A times A transpose, and then this matrix is going to tell us how we should order the graves. So we're remembering that this matrix will tell us, the ijth element tells us how many pottery types grave I and grave J have in common. So for example, here we have the 5, 2 element. That means grave 5 and grave 2 have 2 pottery types in common. That's a pretty strong connection. If the graves have at least 1 pottery type in common, that's some connection. And if they have 0 in common, then they're probably far apart on the timeline. These diagonal elements here are not super helpful because they're really just telling us how many different types of pottery are in each grave. And then these numbers down here are, it's because it's a symmetric matrix, they're a mirror image of these numbers up here. And so really we only need to concentrate on these numbers. They'll tell us everything we need to know about how we could possibly order these graves. So I'm going to read off of this matrix all of this information about 2 graves at a time and the number of pottery types that they have in common. So graves 1 and 2, right here, the 1, 2 element of the matrix, these 2 graves have 0 pottery types in common. Graves 1 and 3 have 0 pottery types in common. Graves 1, 4 have 1 pottery type in common. And graves 1 and 5 have 1 pottery type in common. Graves 2 and 3, let's see, 2, 3 right here, have 1 pottery type in common. And graves 2 and 4 have none. Graves 2 and 5 have 2 pottery types in common. That's strong connection. And then graves 3 and 4, 1, 2, 3, 4, have 0 in common. And graves 3 and 5 have 0 in common. And the last 2 that we needed to catch were graves 4 and 5 right here. And they have 1 pottery type in common. Okay, so we have all this information. Let's kind of look at who should be close together chronologically. For sure, graves 2 and 5 look like they need to be close together because they have the most pottery in common. Let's look at who else is related to 2. So 2 and 5 have these. 2 and 4 don't have anything together, but 2 and 3 have something together. And so 2 and 3 should be close together. Interestingly, 3 and 5 have nothing in common, so it'd probably be a good idea, maybe the relationship is something like this. Let's see who's linked up to 3. So 3 and 1 have nothing in common. We know 3 and 2 have that one thing in common. 3 and 4 have nothing in common, and 3 and 5 have nothing in common. So 3 is probably just kind of out here on its own. 3 to 2 to 5. Let's see what's going on with 5. Okay, 1 and 5 have something in common. We already knew 3 and 5, and 4 and 5 have something in common. So what about 4 and 1? They have something in common. So let's see if this is a possibility for the ordering of graves. And we've talked before about we don't know whether it goes this way or this way, but these are the kind of the connections. So let's just double check our work here. Okay, so let's go down this row. 1 and 2 aren't that connected, and that makes sense here. 1 and 3 aren't very connected, and that bears out with how we've ordered things. 1 and 4 are pretty connected. 1 and 5 are sort of connected. Okay, this could be closer, so that may be something we need to change right there. But let's keep going. 2 and 3 are connected. 2 and 4, not very close, and that shows up because they're kind of separated by chronology here. 2 and 5, we knew that 2 and 5 needed to be right next to each other. 3 and 4 don't have anything in common, and chronologically they're kind of far away too. 3 and 5 should be kind of far away, and then 4 and 5 need to be together. Okay, so that checks out. The only funny thing is that 1 and 5 do have something in common. So what if we did it, what if the ordering was something like this? Let's double check this. Okay, 1 and 2 should be separated. 1 and 3 should be separated. 1 and 4 should be together. 1 and 5 should be together. 2 and 3 should be together. 2 and 4 should be apart. 2 and 5, of course, need to be together. 3 and 4 need to be apart. They don't share anything. 3 and 5 should probably be apart. And then 4 and 5. Okay, so again, we run into this problem. So we're not sure which way this one really goes with the 1 and 4. In reality, it could be something like 5 is connected to 4 and 1. Maybe they're kind of close to the same time period. But either of these would be acceptable solutions for a chronology of these graves. So a possible ordering of these graves is this way. We don't know which direction it goes. We don't know that 3 is the earliest one. It could have been that 1 was actually the earliest one. So we have to think it may be going this way actually in time. We just know relative to each other that they're sort of close like this. But we decided that in reality that 1 and 4 could have been swapped. So we have to consider that this is a possible ordering or its reverse. And you look at these and you say, well, you know, that's 4 different possibilities. Have you really, is that really helpful? So here, of these 4 probable grave chronological orderings, is it helpful? Absolutely, because in reality, these 5 graves could have been ordered 120 different ways. If you look at all the possibilities, all the possible ways to order these 5 graves, there's actually 120 possibilities. So to be able to narrow it down to 4 orderings is definitely helpful. And we'd have to use other, you know, the archaeologist is going to have to use other clues to kind of narrow it down from here. But this gives us at least a really good place to start. So in reality, there are 120 possible orderings of these 5 graves. And what we've just done is given the 4 most probable orderings of their chronology. All right, we need to go back to the question that they asked us, or the job that they asked us to do. Determine a possible chronological ordering of graves. We totally did that one. We're done with this. But then they also ask us a chronological ordering of pottery types. So here we're not asked to say which graves came first, like on the timeline, you know, of history. We're asked to say which pottery types came first, second, third, fourth. When we label them pottery type 1, 2, 3, 4, we have no idea which one, you know, came in 6500 BC and which one came in 2500 BC. We're just labeling them these numbers as they're being discovered. But just as we were ordering the graves chronologically, one job of an archaeologist could be to order these different pottery types chronologically. So maybe, you know, pottery type 5 came really early, and then it was pottery type 2, and then pottery type 1. And we're going to use a similar treatment of this matrix to order these pottery types. And so at this point, this seasoned archaeologist makes this important assumption, which is that the more graves that 2 types of pottery have in common, you have these 2 types of pottery, and they show up in graves together at a certain rate. The more that happens, the closer those pottery types are chronologically. If there's 2 types of pottery that you never see in a grave together, then they're probably separated kind of far on the timeline. But if there are 2 types of pottery that, wow, they keep showing up in the same graves, not always, but over and over again, then you can assume that those 2 pottery types must be somewhat close chronologically. So be sure and take a minute here to understand the distinction between this and what we were doing before. Before we were ordering graves, but now we're ordering pottery types. And we're really going to use the same matrix, but we're going to reverse the order of how we're multiplying things. We're actually going to look at the transpose of this matrix as our main matrix, and then the transpose of the transpose, which is back to the regular matrix, will be that second matrix that we multiply that's in the product. I'm going to take this first row, first column, and I get a lot of zeros, 1 and another 1. So I've got 2 for this first element here. Then when I take this first row and this second column, I get 1 times 0, 0, 0, 0, 0, 1. Okay, let's think about what this 1 represents. It represents pottery type 1 and pottery type 2. And wherever they both have a 1, that means they were both showing up in that grave. So pottery type 1 shows up in grave 5, and pottery type 2 also shows up in that 5th grave. So the fact that they were there together means that chronologically they must have been somewhat close together, those two pottery types. They don't show up in common in any other graves, but they are together in this one grave. So we can assume here that pottery type 1 and 2 are close together somehow on the timeline. And that's what this 1 represents. Okay, I'm going to go ahead and do the rest of the row. If I get row 1 with column 1, this is going to compare pottery type 1 and pottery type 3. And they have grave 2. They both show up in grave 2, and that's it. So they have at least one grave in common. And then last guy, pottery type 1 and pottery type 4, they both show up in grave 2. And they both show up in grave 5. So pottery type 1 and 4 have a pretty strong connection. This is the resulting matrix, and the ijth element of this matrix will count the number of graves that pottery I and pottery J both show up in. So here we have the 3, 4 element, which tells us that pottery 3 and pottery 4 both show up in one grave. We see them both in at least one grave. Okay, pottery types 1 and 2 show up in one grave together. Pottery types 1 and 3 show up in one grave together. Pottery types 1 and 4 show up in 2 graves together. 2 and 3 show up in no graves together. They're not very strongly linked. And pottery types 2 and 4 show up in one grave together. And pottery types 3 and 4... This should be 2 and 4, and then this is 3 and 4. 3 and 4 show up in one together. Okay, we're all good. Let's go ahead and figure out the order now. So 1 and 4 are very strongly linked because they show up in 2 graves together. And then let's just see what else is going on with 3 and 2. So one thing we know is that 2 and 3 really don't appear to share much in common. So what if we did something like this? Let's see how this checks out. Okay, 1 and 2 need to be together. They are. 1 and 3 should be together. That didn't really work out, but they're not too far apart. They're just one step away. 1 and 4 need to be together for sure. These guys just need to be stuck together like glue. 2 and 3 are going to be apart. And then 2 and 4, that's another problem. They're not exactly together, but they're not exactly that far apart. And then 3 and 4, that checks out that it should be together. So we do have a few, just like any real life situation, not everything works out exactly perfect, but we know 1 and 4 should really stick together. Maybe this is a possible chronology. So let's check out this and see how it works. Okay, 1 and 2 are not together, but they're not totally apart. 1 and 3 need to be together. That's good. 1 and 4 are together. 2 and 3 need to be apart, and they are. 2 and 4 are together, and then 3 and 4. So they're not exactly together, but they're not the furthest that they could be. So these are probably the 2 most likely chronologies, and they could go either direction, so we'll indicate that. And so here are the 4 probable chronological orderings of the pottery types. These 2 are the same, just opposite directions, and these 2 are the same, just opposite directions. So today's big ideas are really the idea of a transpose of a matrix, and along with that, matrices which are symmetric, which means their transpose is the same as the original matrix. These are really an important class of matrices. We mentioned what the trace of a matrix is, and this important application in archaeology.